Hi, my name is Jayant D'Souza. I'm the Technical Product Director at Siemens EDA for Yield Learning Solutions. Today, I'm going to talk about a feature that we have called high resolution chain diagnosis. But first, let me start with an introduction and background. I'll go through a scan chain diagnosis overview. I'll talk about the three different aspects of high resolution chain diagnosis, and then I'll draw some summary and conclusion. Scan chain diagnosis has been used to identify systematic defect mechanisms during NPI and yield ramp for a number of years. Scan chain diagnosis identifies identifies defects using failing test cycle information and provides coordinates and layer details for each suspect defect location. Now, newer trends in advanced nodes, so things like backside power down, backside power rail, sometimes refer to the same technology, have made electrical fault isolation extremely challenging and may be even impossible in some cases. So for chain diagnosis, what this translates to is being able to, as a requirement, to be able to produce a single suspect diagnosis report so that actionable physical failure analysis can actually be performed. So what really drove all of this? There's another aspect, overarching feature aspect of and trend that we've seen in scan diagnosis in advanced nodes. There has been a steady shift towards chain diagnosis, towards chain fails being a more predominant piece of the population. In pre 7 nanometers technology nodes, it was pretty common to have, up to 70% of the initial fails during the early ramp and new product introduction to be chain failures, chain defects. And as those were ironed out, as those were sorted out, those systematics were sorted out, we'd see a kind of switch between the logic and the chain fails. However, what we've noticed in the lower technology nodes, this is even before backside power, the more advanced technology nodes like 5 nanometers, 4 nanometers, is the chain fails or the chain defects stay at a stubborn 60%. So 650 to 60% of the failing defects, even when it gets to a mature part of the product life cycle. So those two factors, one is this trend that we've been observing over several years in several technology nodes, and the fact that new technologies like backside power rails are coming that are going to make EFI really complex, have fed into everything where chain diagnosis is going to be a really predominant piece of defect isolation and defect identification. EFI complexity itself has grown pretty significantly, and EFI there are lots of great techniques to do EFI before physical failure analysis. It can make failure analysis really accurate, and it really does make the PFA count finding a defect mechanism. But in selecting dies for FA, generally single suspect cases of chains account for about 15 to 25% on average across the industry, are go directly to FA. If you have multiple suspects, then you generally go through some kind of EFI cycles to isolate the defects to a very specific region on the chip before PFA can be performed. But as the optical resolution limits are reached at these smaller geometries, these EFI techniques like LVX become challenging, if not almost impossible. So so essentially, in summary, the defect trends that drive chain diagnosis at advanced nodes, like new persistent defect locations in the back end of line, like in the global control signals, those are the ones that are causing this. Those are some of what is causing the population of chain defects to be stubborn at that stubborn 50, 60%. There's new persistent defects in the front end of line, so defects inside of cells that are causing scan shift failures. And I'll talk more about some technologies that can be used to address it. And of course, this increasing complexity of the localizing the defects, right, for technology like backside power down. So these kind of things have ultimately ultimately converged and really have asked us have posed the question: can the current simulation-based chain diagnosis techniques be leveraged to diagnose these new persistent defects, and even better, produce better resolution with a smaller defect area to enable successful physical failure analysis? So to answer that question, I'm going to introduce different pieces of technology, and I call them high resolution chain diagnosis. So there are three different pieces of technology. There's layout aware chain diagnosis, global control signal diagnosis, and cell aware chain diagnosis. In the next few slides, I'm going to talk about a little bit more about each of them. But first, I'm going to start with the scan chain diagnosis overview. So first, what is scan chain diagnosis? So scan chain diagnosis is a simulation-based technique to identify defects that cause scan chain shifting to fail. Chain diagnosis primarily consists of identifying the failing scan chain, identifying the defect on the scan chain that's failing, and then identifying the failing cells on that defective chain. Chain diagnosis itself uses both failing chain test patterns and failing scan test patterns to arrive at a diagnosis result. So how does the simulation tool, identify a failing chain and defect type? So from the chain test, so the chain test has no capture, the tool can identify the tool can identify based on the loaded values. You expect when you load in a certain sequence into the chains, you expect the same sequence to be loaded out with if there was no capture, once you account for all the inversions and things like that inside the scan chains. However, if you have a defect like a stuck at one, you'd likely observe the equivalent of all logical ones being shifted out, accounting for all inversions, and of course in the scan chain. And similarly, if you have a whole time defect inside of a scan chain, you might see a shift in the value between 0, 1 value, a slow to rise kind of defect. So that kind of observation helps identify, just using the failing chain test patterns, identify the failing chain and the failing defect and the defect type in that chain. That information is then leveraged to locate the defective scan cell in the chain. So in a scan test pattern, values are shifted into the scan chain. There's a capture cycle, one or more capture cycles where the circuit is put in functional mode and the response captured of the circuit. And once you capture, even though the initial loading was bad let's say you have a stuck at one in a scan chain and it loaded some of these cells loaded to the wrong expected value. Post capture, some of the bad values propagate to other scan chains and are observed on other scan chains. Using that information, and then once we shift out, while the tool has already identified from the chain test patterns exactly which chain and what defect type what failing chain occurred and what defect type occurred on that scan chain, it can then observe the failing cycles on the other chains and use that information to better resolve which scan cells in the chain are actually causing the defect in the design. So that, in a nutshell, is scan chain diagnosis. Scan chain diagnosis itself requires unidirectional scan chains in the design. It requires AT failure logging of both failing chain patterns and failing scan patterns. And it's been used for over a number of years to produce accurate results that localize the defects to either a scan cell or a group of scan cells on a defective chain and its associated nets. With that brief explanation, let me now switch to discussing what these three different pieces of technology that I mentioned earlier. The first of which is layout-aware chain diagnosis. Layout-aware chain diagnosis is really to detect and diagnose defects that are opens and short defects in the interconnect between two scan cells that cause a scan chain shifting failure. So these interconnect defects that occur on the path between scan chain in between different scan cells in the scan path can sometimes cause scan chain shifting to fail. The defect is not necessarily in the scan cell. It is in the path between the scan cell and the logic. But chain diagnosis in the past would narrow down the scan cells, observing the failure and all the relevant input and output paths. So it would be accurate, just not highly resolved. That is, the area to go and search in PFA was larger. So to illustrate this a little bit more, let's consider an interconnect defect that's affecting the scan chain shifting. So think of a bridge between two scan cells that between two scan cells in the net between two scan cells that's bridged to something in the logic. During shift, the scan cell is loaded with a one. Okay, the bridge to ground on the interconnect drives that one to a logical zero. So this causes the scan chain shifting to fail for the scan chain. The scan chain diagnosis identifies the scan cell and its output paths as defective candidates. However, the defect is not in the scan cell, but actually it's in the interconnect path, as we just saw. So layer-aware diagnosis uses physical net information and characteristics to isolate the failing net segments with accurate defect type classification. So it uses the layout database that it was used for logic, but it has all the information even for the chains, and it leverages that information and to identify the failing net segments that could be causing the shifting to fail. So the layer-aware chain diagnosis flow is no different from a typical scan chain diagnosis, a scan diagnosis, logic diagnosis flow that's layout aware. No extra additional information is needed other than providing a layout database which already exists in order to do logic diagnosis anyway. Another very quick illustration of some more illustrations of how layer-aware chain diagnosis works. These are a couple of injected cases where the defect was injected in the path here between in one of the paths, and with layer-aware chain diagnosis with the baseline, you see that the driving scan cell with all of its branches. However, with layout-aware chain diagnosis, the tool can isolate the failing branches. In this case, the defect was injected in this segment of the net, and as you can see, the tool has identified only these two failing branches and says that this one branch is passing, thereby improving the resolution. What that looks like in the layout is that in the past you'd have two fairly large nets, and one whole section of the net is removed, and only one portion of the layout net is retained now in the new technology. Another example of this technology is the layer-aware chain diagnosis, where a number of fan-out chains, fan-out cells were identified, and here's where we have identified bring it down to a single cell and a single output, because the new analysis of in this case there was an open on the net, and the tool can correctly identify the net segment that's causing this to fail. And what this boils down to is a very specific net segment. Instead of all of these nets showing up in the layout, you have only a specific net segment that's identified by this new simulation technique. We've also run this in volume over a large set of injected benchmark cases, and we see a 1.5x reduction in suspect area. And we've also seen direct correlation to PFA using this technology. The next thing that I want to talk about is global control signal diagnosis. Global control signal diagnosis are defects in global control signals like clocks, scan enables, sets, and resets. Again, this is also focused on the back end of line defects. So things like clock sets and resets are a very large part of digital infrastructure and the design. And if you have a defect like a short or open on these signals, you can cause scan chain shifting to fail. So in the past, these would just manifest as a catastrophic failure of multiple scan chains failing at the exact same time. And so the typically people would rely on triaging this kind of defects using a combination of FI and FA. However, with modern designs, one of the things that's changed is these defects in the global control signal network can have a very localized effect. So let's illustrate this technology a little bit more. Think of a root clock that drives a clock tree that's driving a bunch of scan chains. You have the root clock that's driving a bunch of these scan chains, and let's say you use scan in a 1100 kind of sequence into each of these scan chains. If you had a defect in one branch of the root clock, you would this would cause two of the chains to fail, but not the third chain to fail. And this causes catastrophic failures because the clock doesn't actually pulse and doesn't actually it doesn't the scan cells don't actually load. So with the current clock tree diagnosis, we can isolate it to a very specific net segment in the root clock from the root clock to identify what was driving. Instead of seeing two different chains failing, we can identify it to this very specific net segment. Again, for this piece of technology, the only additional piece is a control signal database that gets automatically created and extracted from the layout database and the design, and no additional information other than that is needed to perform this diagnosis. So here's an example of how a defect on a scan enable can cause multiple scan chains to fail. If in the baseline, a defective scan enable signal caused 30 failing chains to show up in the diagnosis reports because all the 30 scan chains unload the wrong values. However, after using this new kind of simulation technique with this control signal database and analyzing the signals in there, we can isolate it to a single logical suspect in the scan enable path. Scan enables, as I mentioned, and any of these global control signals in modern designs can also have a localized effect. So sometimes you can see only a single scan chain failing with a few suspects. However, the defect is not in any one specific one of these scan cells. It's just that the buffering in the scan enable tree can cause these three cells to fail in exactly the same way at the same time. However, once we use using this new technology, this can be isolated to a very specific and actionable set of nets on the scan enable tree that can be used for FA. So for this technique, once you use this technique, actionable results for FA look like a very specific set of polygons and layout locations that have to be analyzed further with layout layers as just in a very familiar layout-aware diagnosis format. So the diagnosis that is produced results in a scan-enabled callout, which is a very specific set of nets, not in the three cells. If FE had looked at the three cells, they might not have found that particular defect area. So global control signal diagnosis has been shown in silicon to increase the number of FA usable diagnosis cases. About 30% of cases with multiple failing chains were found in a large volume silicon study that we conducted with some of our industry partners. We found about 30% of the cases with multiple failing chains have a control signal defect. 57 new additional, once we deployed this technology, 57 new additional single suspect chain diagnosis reports were achieved from a silicon study of over 1,000 diagnosis reports. So that basically has the impact of being able to skip fault isolation completely for those cases. The third piece of technology that I want to talk about in high resolution chain diagnosis is cell aware chain diagnosis. So cell-aware chain diagnosis is a piece of technology that's focused on front end of line defects, that is things inside of the scan cell that could cause scan chain shifting to fail. So these are think of multi-bit flops and defects and inside multi-bit flops in that can cause the scan chain shifting to fail. So scannable flops, multi-bit flops, MBFFs, if you will, they comprise a very large majority of scan chains for modern designs. The defects in the shift path of multi-bit flip-flops can cause scan chain shifting to fail, and it's very hard to isolate because these defects are inside the scan cell, and there's no visibility inside of the standard cell. The multi-bit flop is a standard cell in and of itself, and there's very little visibility inside it. So this new advanced technology can isolate transistor level information inside the multi-bit flip-flop and identify the shift and capture behaviors of the individual transistors. So in order to use this technology, the only additional piece of information that's needed is a newly created UDFM file using our cell model gen tool. It can accurately extract the shift and capture path information inside the scan cells during the cell model gen UDFM creation process. So defects inside the scan cells as part of this will get called out. That cause scan chain shifting to fail will get called out, and its physical characteristics, the layer it's on, the polygons associated with it, will all get called out in a diagnosis report. So the internal cell suspect area is really what happens in this technology is really reduced by using this pre-characterized transistor behavior. The pre-characterized transistor behavior is extracted by cell model gen and stored in the UDFM file that's provided to diagnosis. The shift path information for the UDF is also stored for each of the cells. An illustration of this is when cell-aware chain diagnosis run, it can be used to isolate the defects inside the multi-bit flop standard cell boundary itself. The defects that affect the shifting operation of the flops and control lines can also be identified. So this is even clock and sets and resets inside the cell multi-bit flop can also be identified. There's up to what we've seen in a large volume silicon data set is there's up to 20x cell internal suspect reduction of multi-bit flops because, as I mentioned before, the multi-bit flops comprise a very large number of the large population of the scan cells in modern designs. On an average, we also observed about a 5x reduction in cell internal suspects for all standard cells. So instead of calling out the entire standard cell, we could isolate it down to a very specific set of cell internal suspects. This technology reduces the fault isolation requirements very significantly, because even in a case of in this case this entire box is a 4-bit multi-bit flip-flop, we could isolate it down to a very few set of traces on a couple of layers inside of the scan cell. So this is an example of something that was taken from that we found in silicon, where we isolated this down to a very specific region of the scan cell where the defect was found. One of the key metrics of chain diagnosis is how many single suspect diagnosis cases you can obtain. With this new technology, these three pieces of new technology enabled, in a high volume silicon study, we found on an average at least a 21% increase in just the baseline cases, and in overall, a cell-aware chain diagnosis itself accounted for about 28%, an increase of 28% cases that impacted 7% of those over 1,100 die that we ran diagnosis on. There were also some key core algorithm enhancements and layout-aware chain diagnosis that also accounted for another 4%, and global control signals, as I mentioned, accounted for another 5% of the total that were multiple failing chains or even a single failing chain with multiple cells, which we isolated down to a single suspect. That leads to a 1.8x improvement in resolution in single suspect resolution cases. And in summary, this high resolution chain diagnosis flow follows the standard chain diagnosis flow, nothing different. It comprises three pieces of technology: cell aware chain, global control signal, and layout aware chain diagnosis. This piece was completely validated in high volume silicon experiments and show a 1.8x increase in the number of single suspect chain diagnosis cases, thereby improving PFA workflows. Thank you.